Okay, hi everyone. So I'm Ron Rothblum, and this talk is titled Proving as Fast as Computing, Succinct Arguments with Constant Prover Overhead, and this is a joint work with Noga Ron-Zewi. So this talk is about succinct, very short proofs. So the setting that I want you to have in mind is the following. We have some NP language L that we're interested in, and the verifier is given some statement X and wants to check whether X belongs to L or not. To do this, the verifier is allowed to interact with a prover who knows X, and in addition knows, let's say, a satisfying witness showing that X is in the language. So of course, the prover could we're looking for our prover to convince the verifier that X is satisfiable. And of course, the prover could just send over the witness. But the point is that we're looking for proofs that are much more efficient, in particular with much shorter communication, and ideally also with super fast verification. Okay, so that is the setting of succinct proofs. And I want us to start off by saying that the study of the efficiency of verification has really been at the heart of theoretical computer science, basically since the inception of the field. So if you look at the notion of an NP proof, it's about efficient verification, right? And as the field progressed, we've had more elaborate notions of proofs, interactive proofs, multi-prover proofs, PCPs. And as our understanding of the notion of a proof developed, we've also had sort of amazing results that accompanied this, ranging from the theory of NP completeness, zero knowledge proofs, the PCP theorem, and so on. So really the study of proof systems has been a major catalyst in the development of the theory of computing. So very important in theory, but something that is, I think, pretty unique and interesting is that this area is also drawing immense interest also in practice, and especially within the context of blockchains and cryptocurrencies, where this is drawing really a ton of interest. And it turns out that these proof systems, especially if they're also zero knowledge, which we'll mention in a few slides, these have amazing applications. And I'm a theoretician, I would have a hard time explaining exactly what these are, but we can take the word of a very central figure in this field, Vitalik Buterin, who is one of the leaders in this area, who says that this is one of the most powerful and important cryptographic technologies of the past decade. Okay, so this is drawing a lot of interest also in practice. And as we are starting to develop such proof systems also in practice, we are starting to identify what are the bottlenecks. And one of the key bottlenecks is really in the complexity of generating the proof, which in practice is still orders of magnitude slower than just directly performing the computation. Okay, so this is a problem. And the fundamental question that we would like to answer is, can proving be as fast as computing? Okay, can we prove as fast as if we were to just directly verify the relation? And something that I want to emphasize is that in this work, we're going to be looking at very small factors, so even smaller than logarithm factors, constant factors. And in this setting, the computational model really matters because when transitioning between different computational models, there's usually overhead, typically at least logarithmic overhead, which is not something that we can afford. So we are really focusing on small factors, and the computational model really matters. And in this talk, we're going to focus on the setting of Boolean circuits. So Boolean circuits, as you all probably know, are can be represented as a directed graph. We have the leaves, which are these layer of nodes at the bottom, which you think of as inputs. And then we have the internal vertices, which are gates, marked in this example by and, or, and not operations. And you evaluate the circuit in the natural way. So we're going to be looking at constant fan-in, constant fan-out circuits with arbitrary gates. And I should mention that the study of the exact Boolean complexity of cryptographic primitives and protocols was initiated in this beautiful work of Yishai Kushilevitz, Ostrovsky, and Sahai. And if you're wondering why look specifically at Boolean circuits, first of all, I want to say that it's an extremely natural and very basic model of computation. I'd argue that it really captures the intrinsic complexity of a problem. So if you were to compare it, for example, to looking at computations over a RAM, then you need to start arguing what operations are valid on the RAM and what aren't, and so on and so forth. Another model that people have looked at is looking at arithmetic circuits. So same sort of picture, but all the computations are over some large finite field, and the gates correspond to field operations. And we have, I'll mention it in a couple of slides, we have great results in the arithmetic setting, but it doesn't, so it does a good job capturing arithmetic computations. But if you want to capture a Boolean computation, say evaluating the SHA hash function, which is very Boolean, then you'd have to emulate the Boolean field over the larger field, and this is wasteful. Good, so we're focusing on Boolean circuits, and without further ado, we can go to the definition. So as I said before, we're fixing a Boolean circuit C. We have our verifier, which is given an input X, it's part of the input to the circuit, and the prover P is given X, and the other half, or the other part, which is the witness, and they interact. The requirement is that if C of X is satisfiable, there exists a corresponding W that satisfies the circuit, then when they engage in this protocol, our verifier accepts. The soundness requirement says that if our circuit is unsatisfiable, then no matter what a cheating prover might try to do, as long as it's a polynomial time cheating prover, it will only convince our verifier to accept with some small probability, epsilon. This epsilon is what we call the soundness error of the protocol. And something that I should mention is that we are restricting sounds to be sort of computational, in contrast to sort of the classical interactive proof notion, which allows the cheating prover to be unbounded. But it turns out that if we're looking for a sort of succinct communication, that this is inherent. We cannot achieve sort of perfect soundness against unbounded provers. Okay, so as I started off the talk saying, we want the communication to be much shorter than the witness length. In addition, and this is sort of, in a sense, optional, we would like our protocols to be zero knowledge, which means that when interacting with the prover, the verifier learns nothing more than the fact that the input X belongs to the language. This is, of course, a very desirable property, but it turns out that you can, first of all, the notion of succinct argument is interesting even if you don't have zero knowledge. And secondly, once you have a succinct argument, it turns out that there's a simple method for making it also be zero knowledge. So you can sort of tack on zero knowledge for free, which is what we're going to do. So zero knowledge as part of the definition is sort of optional. Okay, so before telling you what our results are, let me mention some prior work. So first of all, if you really don't care about small factors, you're happy with a prover that has polynomial overhead, then this question has been solved for 30 years. Okay, so fundamental results of Kilian and Mikali show how to do this with polynomial time prover based on the PCP theorem. But in recent years, last decade or so, we've had dramatic improvements in the efficiency. So the state of the art is that if you're looking at Boolean circuits, you can do it with polylogarithmic overhead. So S is the size of the circuit, and you can have the prover be implemented in S times polylog S. If you restrict to arithmetic computations, again, over a large finite field, the field is at least linear in the sizes of the circuit, then we can actually do constant prover overhead. This sequence of recent works has achieved that. So again, this is the arithmetic setting. The last setting that I want to very briefly mention is sort of the non-succinct setting. So imagine that I didn't require the communication to be succinct. So, could just send over the witness. The reason you can't just send over the witness is I do want it to be zero knowledge. So this is also a very interesting setting. And here we've had a sequence of works, which gets very efficient provers. But even here, there are some open questions, which I'll mention at the end. Okay, so moving on to our result, let me start with a very informal statement because I want to highlight some interesting aspect, and then we'll state the result more formally. So informally, what we construct are succinct arguments for general Boolean circuit computations where the prover is linear in the size of the circuit. So that's the main result. And this sort of raises the following interesting question. So if you think of a Boolean circuit, just describing the circuit to you, I have to sort of go over every gate and tell you who the two incoming wires are or where they're coming from. So just describing a Boolean circuit is, super linear in the size of the circuit, which is weird, right? How can our prover be smaller even just in just the description of the circuit? And the answer is that, in previous works, usually you had like a single prover, which was given, X, W, and the circuit, and was implemented, at the very least in time linear in the circuit description. What we're doing is different. What we show is that for every circuit, there exists a corresponding prover circuit. So basically, the original circuit is hardwired into the prover. And that's how we achieve a strictly linear size prover. Right? So if you have a circuit of size S, then we construct a prover circuit of size O of S. Okay, so having said that, we can move on to the formal statement. So first of all, for this result, we're going to need to rely on a cryptographic assumption. For those who are interested in the sort of gory details, the assumption is the existence of a linear time computable collision resistant hash function. I won't elaborate on this assumption too much. It's a very plausible assumption, and we have candidates for this. Okay, so it's a pretty plausible crypto assumption. And under this assumption, what we construct is a succinct argument for Boolean satisfiability. So fix a circuit C. We're trying to see whether once you fix, C is satisfiable with respect to X. And as promised, the prover is indeed going to have size that's linear in the size of the circuit. Okay, so we have a linear size prover. Our verifier is also linear in the size of the circuit. And I want to say that in a sense, it's inherent and non-inherent. So it's inherent because if you think of a verifier that doesn't read the entire circuit, if you make a small change in the circuit, you could entirely change its functionality, and a sublinear verifier would never notice that. So in that sense, it's inherent. I'll say in a second why it's actually non-inherent and why we can even do better. But naively, it's inherent. The communication is polylogarithmic in the size of the circuit and polynomial in some security parameter, which sort of controls what are the sizes of provers that we are sound against. Well, we think of this as a relatively small value, this lambda. The number of rounds is logarithmic in C. And incidentally, I should say that we're thinking of lambda as being much, much smaller than the circuit size. In particular, the prover and verifier are hiding additive factors in lambda, and there are sizes. But these are just additive in lambda. So the number of rounds is logarithmic in the size of the circuit, and the soundness error is an arbitrarily small constant. So think of 1% or 0.01% or whatever. So at first glance, this sounds like very small soundness error, but actually it's something that we would really like to improve. So what we would really like to achieve is not constant soundness, but negligible or any subconstant, ideally negligible or even exponentially small soundness would be ideal, and that's sort of the remaining main open question in this work. Notice that you can always repeat the protocol in order to reduce the soundness error, but that incurs overhead for the prover, which we don't want. Okay, so that's sort of a key open question. Second point that I wanted to mention, I already briefly discussed, is this theorem says nothing about zero knowledge, not because the protocol is not, we can make it zero knowledge, but it sort of comes for free and in a non-super interesting way, which is why I didn't say it explicitly, but it is zero knowledge. Okay. Okay, so let's go back to this aspect of the verifier. So we said the verifier has to read the circuit. It turns out that in our results, it's sufficient for the verifier to do this in a sort of a pre-processing step. So first, the verifier sees the circuit and does like a linear size pre-processing. And after this pre-processing is done, after it sees the input X and starts interacting, it can be very fast. Basically, just reads the input X and has some additional polylogarithmic complexity. So very fast verification after a linear size pre-processing step. Great. So I want to tell you a little bit about how we achieve this. And the main technical object that we rely on is what's known as an interactive oracle proof. It's a notion that it was introduced independently by Ben Sasson, Kies, and Spooner, and in a joint work with Omer Reingold and Guy Rothblum. And you can think of an interactive oracle proof, or IOP, as sort of a hybrid between an interactive proof and a PCP. So the model is the following. We have, as before, a verifier who wants to know if X belongs to L. And our verifier can interact with a prover. And the way this interaction proceeds is that the prover now sends a very long message. So we're no longer succinct. It's a very long message. And the verifier answers with some random points. Now the prover sends another very long message. Verifier answers with random points. Another long message, and so on and so forth. So far, the verifier didn't read any of the interaction. At the very end, the verifier specifies a small number of bits in the transcript and reads them. And based on that, decides whether to accept or reject, like in a PCP. So a one-round version of this would be a PCP. If the verifier reads everything, it's just an interactive proof. So it's something sort of in between or a mix of the two. Something that I should highlight is that when talking about this model, we are thinking of soundness against an unbounded cheating wizard or prover, okay? So that's an IOP. And IOPs, they were introduced about 6 years ago, and they turned out to be an extremely useful notion. In particular, they're useful as originally motivated by Succinct, Chiesa, and Spooner, and there's been a ton of work since, including this work, which really rely on IOPs to construct more and more efficient succinct arguments. So that's been one of their major uses, let's say. But they've had a lot of uses and have been studied extensively other than that. So in this work with the guy in Omer that I mentioned, we used IOPs to construct doubly efficient interactive proofs. In the previous work with Noga, which actually this work relies on, we managed to construct very, very short IOPs, and they've been used for hardness of approximation. So very powerful and interesting notion, I think. And so for IOPs, we also have a similar result. Let me highlight the differences. So first of all, for this result, we're not making any cryptographic assumption. It's unconditional. Okay, so there exists an IOP for Boolean satisfiability, where the prover, as before, is linear in the size of the circuit. The verifier, also as before, is linear in the size of the circuit, but with preprocessing, it can be also sublinear. The number of bits that the verifier reads is polylogarithmic. The number of rounds as before, and the soundness error as before. So we have this sort of very efficient prover IOP. And it turns out that it's not super hard to show that from this efficient IOP, you can more or less immediately derive the succinct argument. And intuitively, the idea would be that instead of sending this very, very long message, you send a very short cryptographic commitment to it. So on the one hand, it's short. On the other hand, it has a feature of a local opening. So whenever the verifier is interested in querying a point, it can just ask the prover to decommit at that exact point. And it turns out we can construct these kind of succinct commitments that have a local opening, for example, using something like a Merkle tree. Okay, there are actually some nuances in making this work in this constant prover regime, but I won't into it. Okay, so the main technical result is really this construction of the efficient prover IOP. And I want to say just really in a couple of words, what is the novelty here, or what is the barrier that we need to overcome? So one of the most important, celebrated and important protocols in the literature is what's known as the Succinct protocol, introduced by Landford, now Karloff and Nissan in 1990. And viewed abstractly as sort of a problem, the setting that we have is that we have a verifier who is given oracle access to a code word C and is trying to check whether the sum of the message bits of C is equal to some value, let's say is equal to 0. Okay, and we're looking for the verifier to run in time that is much smaller than K, much smaller than just reading all these message bits by interacting with the prover. So maybe aiming for polylogarithmic in K verification time. Turns out that such a protocol is known for any tensor code. This is in the original work of LFKN for the low degree extension and abstracted by Or Meir to general tensor codes. And in this IOP setting, it's also known for the Reed-Solomon code. And this protocol or this problem is really at the heart of many of the fundamental results in the field of proof systems. So starting with the IP equals P space theorem, moving on to MIP equals next, the PCP theorem, or at the very least the original proof of the PCP theorem, double efficient interactive proofs, and so on and so forth. So a lot of protocols are actually relying on sumcheck. It's a very fundamental protocol. In this work, we're going to look at a variant of sumcheck, which we call multi-sumcheck. And the setting here is that we, instead of just one code word, we're given access to two code words. And we want to check that the inner product of the message bits is equal to some value, let's say equal to 0. Okay, so the message bits, their inner product is equal to, say, 0. It turns out that it's really this problem that is being used by all of the previous protocols, but there's in the standard setting, once you have sumcheck, you also have multi-sumcheck. And the reason is that typically the codes that we are using are what's known as multiplication codes, which basically means that if you take the product of any two code words, what you get is another code word of some closely related code. So if your code C is a multiplication code and you want to solve multi-sumcheck, just take the product of the two code words, this pointwise product. Take the pointwise product of the two code words and solve sumcheck. What you will be getting is the inner product, so multi-sumcheck. So basically, all the previous works that I mentioned really are relying on multi-sumcheck. The problem that we are faced with is, so in all these previous works, more or less, at a high level, the computation itself is encoded by a multiplication code. And the problem that we're faced with is that we don't know any linear time encodable multiplication codes. Okay, so we cannot afford to encode the computation. We're aiming for a constant proof or overhead. We cannot afford to encode the computation with multiplication code, basically. So really the main technical idea in this work is constructing a linear time encodable code C, which is actually not a multiplication code, but it is multi-sumcheckable. So we construct a protocol for verifying that the inner product of the messages of the two code words is equal to 0 or to some scalar. Okay, so linear time encodable C, that is not multiplication code, but it does support multi-sumcheck. Okay, so for those of you who are interested in how we do this, then you're welcome, of course, to read the paper or to reach out to us, and we'll be more than happy to tell you more about it. So let me sort of conclude with a summary and then some open questions. So first of all, as mentioned, what we show is that we have succinct argument for Boolean satisfiability with constant prover overhead. The prover is linear in size of the circuit. I didn't get a chance to go into the details, but the main technique that we rely on is something that's called code switching, which we introduced in this previous work with Noga from 2 years ago. And this technique has also been used in some follow-up works. But both in our work and in the follow-up works, there was sort of a sharp transition from multiplication code into some like high rate or linear time encodable code. So one sort of sharp transition. In contrast, in this work, what we're doing is a much more gradual process. So we keep doing this sort of code switching, but a very mild code switching done many times. And that's how we construct our multi-sumcheck protocol. So let's conclude with some open problems. So first of all, as I said, the main open problem is achieving subconstant or even negligible soundness. This is actually open even in the non-succinct setting. So if you're looking at Boolean circuits, and you allow the communication to be as big as the circuit, but requires zero knowledge, then this is not known. So that's open. One approach for solving this is by developing a linear time encodable multiplication code. That would be fantastic. But maybe there are other ways. And let me mention a follow-up work with Justin Holmgren, in which we achieve such protocols which actually have sort of exponentially small error, 2 to the minus lambda error. This is something that you could achieve by just repeating the protocol from the current work poly lambda times, but that would introduce poly lambda overhead. And instead, what we're doing, we're achieving the same type of error with only polylog overhead. And we can do this not for all circuits, but for a very large and interesting class of circuits. Okay, so that's the question about the errors. So verifier complexity, we said that in the pre-processing model, we can get sublinear verification. It would be interesting to show sublinear verification without pre-processing for uniform computations. That seems plausible and is open. Our protocol is highly interactive. It has logarithmically many rounds of interaction. It would be great to reduce this, ideally achieving a non-interactive protocol. And I should say that this is something that we don't know how to do even heuristically. So typically you would want to, if you're happy with heuristics, you could do something like apply Fiat-Shamir, but we're in this constant error regime in which Fiat-Shamir doesn't work. So even heuristically, I don't know how to achieve this. Lastly, I mentioned that we can sort of get zero knowledge for free, but doing so involves sort of making non-black box use of cryptography, which is something that we don't love. A better way to achieve this would have been to develop the IOP itself to be zero knowledge, so that is open. And a work along these lines that works in the arithmetic setting was achieved recently by Burul, Chiesa, and Lu. So I'll end the talk here. Thank you for listening and for your attention. Unfortunately, I can't take questions online, but I'll be happy to answer anything over either Noga or I will be happy to answer any questions over email. So thanks again, and hope to see you in person soon.